Let's do another one. Sokjen flies her kite 100 feet above the ground. The wind causes the kite to move horizontally at a constant rate of 8 feet per second. Okay, so we've got the kite is 100 feet above the ground and a rate of change. The kite is moving horizontally at a constant rate of 8 feet per second. In order to maintain the height of the kite at 100 feet off the ground, Sokjen must allow more string to be let out. At what rate is the angle between the kite and the string changing in radians per second when the string is 200 feet long? So find this rate of change at a particular moment when the string is 200 feet long. So I think for this example, a diagram is particularly useful. So we've got initially, here's my kite. Maybe we'll have a green kite. And this kite is 100 feet off the ground. Here's my ground. And initially, it's right above her. Here's my string. We're making an assumption that it's going from the ground. It's 100 feet, we should say, maybe from her hand, right? She has some height. But there is the piece of string, and it is being let out. So we still have the 100 feet here, but now my kite is moving horizontally. Still have my 100 feet. But my kite has traveled some distance. Okay? So they gave me that the kite is moving horizontally. It's moving this direction at a constant rate of 8 feet per second. Right? So I need to introduce some notation here. I'm going to let x be the distance, and it's fine to say just like the distance as pictured, as opposed to trying to describe maybe the distance that that kite has traveled horizontally since the initial conditions of this story. I'm just going to write let x be the distance pictured. And I also need some sort of introduce a letter for the length of this string. I'm going to let, how about z, be the length of string that's being let out here. So x, it is increasing. Its rate of change is going to be positive. Z is also increasing. That distance is getting longer and longer. And notice right here we've got a right triangle. And then we also need a letter for my angle. We're asked to find the rate at which the angle between the kite and the string is changing. So that's this angle right here. There's that angle. My art is in the way a little. There's that angle. And notice these are parallel lines cut by a transversal. That angle is also showing up right here. But I'll just draw it in the one place. Let theta be as pictured. Okay, so there's my diagram. And now we're going to figure out what the givens and the unknowns are. So what they gave me this rate of change, that the kite is moving horizontally at a constant rate of 8 feet per second. So they gave me dx dt, the rate at which that distance, or x prime if you prefer, is 8 feet per second. And it is in fact positive because that distance is increasing over time. 8 feet per 1 second. And then they've asked us, I think we can write it right here. What have they asked us to find? Here in the dark blue, they've asked us to find the rate at which that angle, theta, between the kite and the string is changing in radians per second. What do we want to do? We want to find d theta dt, or theta prime if you prefer, at a particular moment when the amount of string that's let out is 200 feet. When z is 200 feet. Okay? And now we have to think about how these variables are related to each other. How are x, z, and theta related to each other? I want to pause for a second and have you think about that, and then we'll move forward. Okay, so there are a lot of ways to relate these variables, and I want to discuss some pros and cons. If I look at my picture here, let's say what we're doing. Relate the variables. Right, I want some equation that relates them. We've got 100. We have x. We have z. And this is a right triangle here, and this is the angle theta. And when I'm looking at this, one thing that you might consider is that the cosine is adjacent over hypotenuse. The cosine of theta adjacent is x, and my hypotenuse, wrong color. Adjacent is x, and my hypotenuse is z, and that's all well and fine. But the reason why I'm not going to go ahead and use this choice is because when we differentiate both sides with respect to time, over here we're going to need quotient rule, which is fine. We know quotient rule, but we're going to have a derivative of z, right? We will have a z prime show up in that equation. And it's not that you can't go about finding that, but since z prime is not given, x prime is given, I want to try to avoid using z, right? And we don't, not that you can't do it, but that's going to take a significant amount of scratch work. So instead, I'm going to try to use a trig identity that's going to use that constant 100 and that x, because I have information about x prime after differentiating both sides with respect to time. So if I use that, I've got the tangent of theta, TOA, opposite over adjacent, 100 all over x. This would be fine. But instead, and you're welcome to use it, but instead I'm going to use the cotangent of theta. And the reason why I'm going to use the cotangent of theta, that's the reciprocal of tangent, is because I think it would be nice to have x up in the numerator. Again, not that you can't take the derivative of this, you totally can. But I think this is the nicest. This is fine. And this is fine too, but this is going to be a lot more work when I take the derivative of both sides with respect to time. Not just because of the quotient rule right here, right? It's really because that z prime is going to show up in quotient rule and I got to go find that, right? So this is the relation that I'm going to go ahead and work with. All right, after we relate our variables, what we want to do is we want to take the derivative of both sides with respect to time. Let's go ahead. With respect to time. So I've got cotangent of theta, and I'm going to go ahead and take the derivative with respect to time of the left-hand side is equal to the derivative with respect to time of the right-hand side, and the right-hand side is x all over 100. The derivative of cotangent is minus cosecant squared. The derivative of 100th of x is my 100th. But wait a second, chain rule. X changes with respect to time. I gotta multiply by dx dt, or x prime if you prefer. Right? And now we're going to substitute in the known information and solve. We put colons here. Oh my goodness, your teacher made a mistake. What did I forget right here? Theta is changing with respect to time. I completely caught up in color, forgot to multiply by d theta dt, right? Which is the thing that we've been asked to find, right? That's what we're looking for. Sorry about that. Okay. So we know dx dt, that was given to us at our 8 feet per second, right? That was given. And we're asked to find d theta dt, theta prime, at a particular moment when z is 200. And when I'm looking at this equation, I'm thinking, okay, this is what I'm looking for, but what on earth is theta? To do that, we're going to have to do a little bit of right triangle trigonometry. So I'm going to go off to the side and do a little bit of scratch work and bubble it. My triangle, when z, because we're asked to evaluate this when z is 200. Now remember, cosecant squared is really just cosecant times itself. So maybe I even want to write that this way. Minus cosecant of theta all squared. And that is hidden right there in that right triangle, doing that trigonometry. Let's go ahead and do 8 over 100. So cosecant is the reciprocal of sine. Let's get theta on there. Sine is opposite over hypotenuse, so cosecant is going to be hypotenuse over opposite. The cosecant of theta is hypotenuse over opposite. Hypotenuse all over opposite. Get theta on there. Delightful. The cosecant of theta is just 2. 200 divided by 2. Bubble in our scratch. Okay. So from our scratch, we found out that this value is 2. And so now we're just ready to solve. We've got minus 2 squared, which is minus 4, times d theta dt, the thing that I'm looking for. I think just judging by my space, I'm going to go ahead and use theta prime, is equal to 8 out of 100. We can simplify that fraction, but minus 4 times the thing that I'm looking for is equal to 8 out of 100. The thing that I'm looking for, the rate at which the angle theta changes with respect to time, is 8 divided by 100 times minus a fourth. Theta prime is equal to minus 8 divided by 4 is 2, and 2/100ths is a 50th. Radians per, and what were the time units initially? They were seconds per second. Okay, not the only way to do this problem, but I hope I've modeled for you why I made this choice. Or this choice is fine too, but really this one is so much work, because when I take the derivative low z, d high z, x prime minus high x d low z prime all over low squared, I have a z prime showing up in that equation. And that rate of change, although it's something you can find, isn't given. And so coming here and just working with theta x and the constant 100 makes my life a lot more simple.